Hello everyone, my name is Taciana, Oliveira Souza. I'm a professor at Federal University of Uberlândia. There is a Brazilian public university located in the southwest of Minas Gerais, Brazil. I'd like to thank you very much, the workshop organizer, for the invitation. It's a pleasure to me to talk at 16 International Workshop on Real and Complex Singularities. I studied the topology of singularities, and today I chose to talk about the Milnor fibration and its topology. Thank you very much for your attention, and I hope you enjoy my talk. I'm going to talk about Milnor fibrations and its topology. My presentation is divided in three parts. The first one is the complex Milnor fibrations. The second part is the real Milnor fibrations for unisolated singularity. And finally, I'll talk about Milnor fibrations for a non-isolated singularity. In the book Singular Points of Complex Hypersurface, John Milnor studied singularity of complex hypersurface and showed how to attach a locally trivial smooth fibration to each singular point in order to extract topological data from it. Milnor proved the existence of such fibration structure associated to holomorphic functions and also to real polynomial maps, but in the latter case for isolated critical points. Both fibrations are currently known as the Milnor fibrations. Milnor showed that for a complex polynomial function, there is a locally trivial fiber bundle associated to each point of the hypersurface V. The intersection K is called the link at Z, and each fiber is a smooth to n-dimensional manifold. According to Milnor, the topology of V within the small ball is closely related to the topology of the link. More precisely, the intersection V of V and a small ball is homeomorphic to the cone of the link. When Z in V is an isolated critical point, we have more information about linking and the fiber. In this case, the fiber has the multiple type of a bouquet of spheres. All the fibers have the link as boundary, and the link is also n-2 connected. The link is a common boundary of the fibers, so there is an open book structure. In this example, the link is a trefoil knot and the fiber has the multiple type of a bouquet of 2 cycles. Here, We have an illustration of the deformation from the fiber to a bouquet of spheres. Milnor also showed the existence of fiber bundle structures for real maps with isolate critical points. This restriction of F is a projection of a locally trivial fibration called real Milnor fibration. The total space of the real Milnor fibration is diffeomorphic to the complement of an open tubular neighborhood of the link. The link is the boundary of the fiber, and if the link is not empty, the fiber is P minus 2 connected. Consider this example from R4 to R2. It's easy to see that the fiber is diffeomorphic to a disk. So, the fiber don't have the multitype of a bouquet of spheres. So, we can see a difference of the topology between the real case and the complex case. In the complex case, for an isolated singularity, the fiber always has the homotopy type of a bouquet of spheres. Milnor proposed to call F trivial if the fiber F is diffeomorphic to a closed ball. So the previous example is trivial. Milnor posed the following question: for which dimension do non-trivial examples exist? Church and Lamotte answered Milnor's questions in the following way. Note that they don't answer the question for dimensions 6 and 3. In 2012, Souza, Oliveira, de Matos, dos Santos provided conditions under which an example is trivial for dimensions 5,2, 6,3, and 8,5. More precisely, for dimensions 5 and 2, F is trivial if and only if the fiber is simply connected. For dimensions 6 and 3, F is trivial if and only if the topological degree is 0, and if and only if the link is connected. And for dimensions 8 and 5, F is trivial if and only if the topological degree is 0, if and only if the link is not empty. In 2016, dos Santos, Oliveira, Saek, and Souza answered the Milnor's questions for dimensions 6, 3. That is, they showed the existence of non-trivial examples from R6 to R3. We cannot expect, in general, a bouquet theorem in the real case, since the fiber can be contractible. But for a non-trivial example, for R to P to RP, the real Milnor fiber has the multiple type of a bouquet of spheres. In the last part, I'm going to talk about real Milnor fibrations for non-dissolute singularity. I'll follow definitions and results given by Daisy Massey. Let F be a non-constant analytic map, and we denote by sigma F the set of critical points of F. Let R be the square of the distance function to the origin, and we denote by sigma FR the set of critical points of the path FR. Let us introduce in the Milnor's condition A and B. F satisfies the Milnor condition A at origin if sigma F is contained in V in a neighborhood of the origin. F satisfies the Milnor condition B at origin if 0 is an isolated point in this intersection. In 2010, David Massey showed that if a non-constant analytic map satisfies Milnor condition N and B, then there is a Milnor fibration associated to the map. In 2020, Souza, Santos, and Zapata are working in a prepping to obtain topological data about fibrations under the Milnor's condition A and B. At the moment, we have the following results. If F is a polynomial map that satisfies Milnor conditions A and B at origin, then the total space of the Milnor fibration is diffeomorphic to the complement of a semi-algebraic neighborhood of the link and if P is greater than or equal to, the total space of the Milnor fibration is path connected, and if P is greater than or equal to 3, the Milnor fiber is path connected. Furthermore, for P equal to, the Milnor fiber is path connected if and only if the Milnor fibration admits a global cross-section. Here we have the reference of this talk.